Okay, and next we will discuss the third property of conductor, which is the interior of the conductor have no excess charge in the static situation. We can also write it is that the charge density, volume charge density inside the conductor is 0. Now we already know that when we placed in a conductor, when we placed a conductor somewhere in electric field, then what will happen? Negative charge induced on the surface which is close to the field, negative charge, sorry, these are the negative charge, and positive charges induced on the other surface. If we place this in external electric field E0. Now to prove this property that the interior of the conductor is charge free, no excess charge inside the conductor, the charge density is 0 inside the conductor, we draw a Gaussian surface. Suppose this is the Gaussian surface. Now by definition of flux, phi is equal to integral of E dot dA or ds. Okay, dA is better. Now also we know that from Gauss law that flux, total flux through any closed surface is 1 over epsilon naught times the total charge enclosed by that closed surface. So from this I can write Q over epsilon naught is equal to E dot dA. Now E is equal to 0. E is equal to 0 inside the conductor. Because this was the first property which we proved in the previous video. Since E is equal to 0 inside the conductor, so the flux through the Gaussian surface will be 0. If E is equal to 0, then flux will be 0 through this Gaussian surface. If flux is 0, then we know that flux is basically what? Q over epsilon naught. This will be equal to 0. So this implies that Q is equal to 0. So this shows that there is no excess charge inside the in the interior of the conductor. Now to prove this, that the charge density, volume charge density inside a conductor is 0, we consider the differential form of Gauss law, which is del dot E is equal to rho over epsilon naught. As we know that since E is equal to 0 inside a conductor, so it means that rho over epsilon naught is equal to 0, or rho is equal to 0. So it means that the charges inside the conductor is 0, but the charges are present on the surface of the conductor. Like there is still charges around, like on the edges, but exactly as much plus charge as minus, because if there are, let's suppose, 10 negative electron, then there are 10 positive charges appear, so these charges cancel each other. So as a whole there is no net charge inside this conductor. So this was the third property of the conductor. Next we will move towards the fourth property, which is a conductor is an equipotential. A conductor is an equipotential. What is equipotential? First I will define that one. Suppose we have a point charge here, or we have, let's suppose, a line of charge here. Let's suppose this is the line charge. Now if we move, the potential is bigger here, it is getting smaller, smaller, smaller and smaller as we move away from this linear charge distribution. But if I move on this way, from here to here, from here to here, from here to here, then all these points have the same potential. Same potential. These have different potential. So this surface or this point are equipotential point. We call it equipotential point, like on this point the potential is same. So this is what we call it equipotential. Now a conductor is in equipotential. Suppose this is a conductor placed in electric field, external electric field, E0. So negative charges appear here and positive charge appear here. Now what will happen? Suppose we have 2 points on this conductor. One is at a potential which is 4 volt and the other point is a potential which is 5 volt. If these 2 points of the conductor are at different potential, then what will happen? Electron will move from lower potential to higher potential and positive charges move from higher to lower. So electron will start moving in this way. This movement will continue until and unless these 2 points have the same potential. Now these 2 points become equipotential, but the third point here, it will have a different potential. So it means that this electron will move here and the movement of this electron continue until all these 3 points have the same potential. But the next point has a different potential now. So what will happen? This electron will move in this way and this motion is continuous until and unless all these 3 points have the same potential. So due to this movement of electron, what will happen? This conductor has a resistance. This electron will collide with the ions or with the atoms of the conductor, so it will dissipate energy. So energy will continuously released, which is again the law of conservation of energy. So law of conservation of energy get failed here because we have energy. We didn't give energy, but we got energy. So from where this energy comes from? It's against the law of conservation of energy. So it means that these surfaces of the conductor, they are at equipotential. This surface is at equipotential. It become at equipotential in million part of the second. In a very, very short time of interval, this whole surface of the conductor had become equipotential. Might be there is a potential difference, but that difference will disappear in a million of a second. Now, next we consider the interior of the conductor, whether it is at equipotential or not. For that, suppose we are bringing suppose I can say that let's suppose this is negative charge and this is positive charge, and suppose that a test charge somewhere from infinity is bringing to the surface, and for that I need, let's suppose, 5 joule work, a 5 volt work to bring this charge from infinity to the surface of this conductor. Now if we bring the charge to the interior of the conductor, we also need work done, 5 joule work, because the internal of this conductor is electric field free, E is equal to 0 in the internal. If I need a 5 joule work to bring a test charge from here to here, then in the interior we have no electric field, so it means that there is no opposing force. If there is no opposing force, it means that we don't need any work, because for the work we need force. If F is 0, so it means that we don't need any work. So it means that if we bring a charge from infinity to the surface or in the interior of the surface, we need the same 5 joule work. Now the question is, one side of the conductor is at positive potential is positive, and the other side of the conductor is negative. Then how the two edges are at the same potential? For this, consider the space without conductor. Suppose we have electric field. We consider this electric field. Now the point which is close to the electric field is at higher potential. Let's suppose it is 6 volt. And the point where the electric field which is far away from this source is at lower potential. Let's suppose it is 4 volt. So this point is at 6 volt and this point is at 4 volt, because this point is close to the source of charge and this point is far away from the source of charge. Now once conductor is placed, let's suppose we are placing a conductor at these 2 points, such that the edge is, one edge is at 6 volt and the other edge is 4 volt. Now once conductor is placed, then negative charge appear on the closed surface, on this surface, and positive charges appear on the far from the source of electric field. Now negative charges induce negative potential and positive charges induce positive potential. So these negative charges induce, let's suppose, minus 1 volt here, and these positive charges induce plus 1 volt potential here. Then what will happen? This surface, this point which is already 6 volt potential when there was no conductor, once conductor is placed, then negative charges induce a negative potential of 1 volt. Similarly, this point which is already 4 volt potential without conductor, once conductor is induced, then positive charges appear here. These positive charges induce, let's suppose, 1 volt here. Then overall we have 5 volt and 5 volt of these two surfaces. So from this we can say that all the surfaces of the conductor are equipotential. And the next property, the fifth property, is at the surface of a charged conductor, E must be normal to the surface at every point. And it is also obvious because we know that charges are always induced on the surface, negative, 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 positive, positive, positive. So it means that the electric field is always normal to the surface, because in the interior we have no electric field. Interior is electric field free, while on the surface the electric field will be normal to the surface. So these are all 5 properties which we will discuss in detail and which we already proved in these 2 videos. In the next video I will move to a new chapter, new topic, which is capacitor and calculating the capacitance and energy stored in the capacitor and so many things which we will do in the next videos. Thank you.